Manipulation of a deformable object is a difficult problem for robots. In particular, paper is a difficult object to be manipulated because, in contrast to cloth, it has bending elasticity and plastic deformation. We have been studying robotic paper folding and succeeded in valley triangular folds. However, the paper shape was not accurately estimated, and it was difficult to achieve more complex folds. This is the configuration of the robot system developed. On the left is a 2-fingered hand and on the right is a 3-fingered hand. Each hand is mounted on a 3-axis slider with a 3-axis rotating wrist. The system is equipped with 4 depth cameras. 2 RealSense D435 cameras are mounted on the top and 2 D405 cameras are mounted on both wrists. The system is connected to a real-time paper shape estimator and simulator. This is a processing flow of paper shape estimation. The area of the paper is extracted from the color image and the shape is obtained as point cloud data. However, this data alone is not sufficient for shape recognition because of data missing. To solve this problem, the real-time simulator is run in parallel. Coherent point drift is used for matching of the measured data and the real-time simulator. The paper model consists of masses and links. Springs are attached between adjacent nodes and between nodes one skipped ahead. We use substep extended position-based dynamic substep XPBD to achieve real-time simulation. The elasto-plastic spring mass model uses bilinear plasticity and the kinematic hardening law as the spring's plasticity model. Using the proposed model, we simulated crane folding. The model behaves like real origami even in complex folding motions such as 2 folds, 4 folds, and crushed folds. Paper shape estimation was performed using actual origami paper. Human hands performed the first valley fold and second valley fold. The left side of the video shows the estimation results and the right side shows the actual paper shape. It can be seen that the behavior of the elasto-plastic model is superior to that of the elastic model. We will apply this model to an actual origami robot.